So now, this video provides the overview about the motion of the object on an inclined plane, and basically on how we can be able to analyze the forces acting, on how the Newton's second law of motion is applied in some other aspects. We'll also be looking at the connected bodies, actually a connected bodies, and how the motion is basically being done. And also we have to assume that the surface is a smooth surface where there's no friction force, and also have to consider the surface being rough surface where we have to expect the friction force. So those are some of the things that you should have to understand about by the end of this video. But don't forget to subscribe, like, comment and share, as it is part of the support system to the service that we provide. And basically we make these education contents for you to learn and to enjoy, and the life goes on. So should be that. So first thing we start to understand about what we call as the Newton's second law of motion. So what is Newton's second law of motion? So in a simple term, as Newton's second law of motion, this is actually a law that expresses that in all cases, force is the one responsible for the object to accelerate. Of course, we understand that the force has got several effects on the object. The force can change the direction of the object. The force can make an object to start moving. The force can also cause the deformation and some other effects. But one of the effects of the force on the object is that the force causes acceleration, or the force causes the velocity of the object to change. That is the acceleration. So we should have that. So how should you have the analytical aspects of the Newton's second law of motion? We should have to get. Let's say this is an object of, let's say, a mass m. Let's say this is the object of mass m, and we have the force being applied on the object, let's say given as F. And now because the force F has been applied on the object, and now the object will happen to accelerate towards the direction of the force, and which is given as A. And now according to the Newton's second law of motion, it is stated that the force being applied, it is directly proportional to the mass of the object and its acceleration. We should have that. And if that is the case, we should think of introducing the constant that is given as, let's say, is equal to k mass times acceleration. Assuming k is 1, then what it tells is that the force is equal to mass times acceleration. And now this is what we call as the Newton's second, actually Newton's first law should be the second law of motion, which states that the force that is applied on the object, it is directly to its actually a mass and also its acceleration. That's how we should have it. And where acceleration is given as meter per second square, the mass has to be in kgs and the force has to be in newtons. We should have that. And likewise, if we have the system of several forces being acting, let's say we have the several forces acting, let's say this is F1, then let's say we have the force, let's say F2, let's say we have another force equated as F3, let's say that is the case. Let's say we have the force F4 acting in that way. Let's say we have another force which is given as, let's say, F5 going over like that. And now assuming that the acceleration it is towards this direction, then principle remains the same. Let's say the object is of mass m. And now according to the Newton's second law of motion, it is stated that the force is equal to mass times acceleration. But now because the system is of several forces, then we'll have the summation of the forces on the object is equal to mass times acceleration. So which means we'll have to sum up the forces acting. And now the forces that are acting in the direction of the motion has to be the positive forces. So which means we'll have the F1 plus F2 plus F3, and the forces that are acting against the direction of the motion, they are negative forces. So we have negative F4, negative F5, and which is equal to the mass times acceleration. So this is how we should have the actually a typical case in which the forces acting, there are several forces on the system, So according to the Newton's second law of motion, we'll have the summation of the force. Actually, the summation of the forces acting, will be equal to mass times acceleration. But now, what if the forces acting, they are at an angle? Let's say we have this kind of a case. Let's say we have a case whereby we have this is the object of mass m, and let's say this is the force equated as F acting in it is at an angle, let's say theta, with respect to the horizon. And now, assuming that the object is moving towards this direction, so how should you have the Newton's second law of motion, and that will have the aspects of this motion? And as you can see, the force is acting at an angle. And now we should have, so which means we should have to resolve the force into components to have the component of the force responsible for this typical motion. So how should you have it? We'll have to resolve the force into components, whereby we'll have, for that case, what it does is that, this is these are the components of the force. We have this is the Fy, that is the y component, and this is Fx, that is the x component. So according to the principles of the trigonometric ratios, you observe that this is the opposite hypotenuse, and that is more of, should be a sine. So which means Fy, it corresponds to have it as, F sine theta. So we'll have it as, F sine theta. We'll have it as that. And likewise, Fx corresponds to have it as the adjacent hypotenuse, and that is Fx being given as F cos theta. So understand, what is the trigonometric ratio and how we should have to understand it here. So keep that in mind. Now, as you can see, the force which is acting in the direction of the motion, it is the x component of the force. Therefore, this is the force responsible for the motion and for the acceleration according to the Newton's second law of motion. And which is given as the force is responsible for the acceleration. And what is that force? We have it as Fx, and which is equal to the mass times acceleration, and which is the same as F cos theta, and which is equal to the mass times acceleration. So that's how we should have it. So keep that in mind. And now, what is a friction force? A friction force, this is the force that you act. So a friction force, this is the force of opposition to the motion of the object between the two contact bodies that are in motion. That's why they call them as the friction force. So we have two types of friction forces. We have what they call as the, a kinetic friction force. So we have what they call as the kinetic friction force. So what is the kinetic friction force? So what is the kinetic friction force? Kinetic corresponds to the motion. So which means the kinetic friction force, this is the friction force associated with the moving objects. That's what they call as the kinetic friction force. And basically it is given as Fk, and which is equal to mu k times the normal force, where this is the kinetic friction force, and this is the coefficient of the kinetic friction, and this is the normal force. So that is the formula for the kinetic friction force. It is the friction force associated with moving object. So whenever the object is moving, the friction force in that case, it is said to be the kinetic friction force. And now we have another friction force, which is said to be the static friction force. So what is the static friction force? As the name itself suggests, static means at rest. So this is the friction force, that keeps an object at rest. In other words, it is the friction force associated with the object being at rest. So that's what we call as the static friction force. Whenever an object is at rest, the force that keeps that object to be at rest, we call it as the static friction force. And basically it is given as Fs, that which is given as the mu s times the normal force, where mu corresponds to the coefficient of the static friction, and this is the static friction force, and this is the normal force. And in all cases, mu k and mu s. You know, a mu k is always less than the mu s. So mu k is always less than mu s. So we should have that. So we have two types of friction forces, the static friction force and the kinetic friction force. And the static friction force associated with object at least. And the kinetic friction, it is the one in which the object, it is the one that exists whenever the object is moving. We should have to keep that in mind. And let us see how we can be able to apply the concept of the motion of the object on the inclined plane and appreciate how we can have everything in order. Let's say we have this is a typical friction force, should be inclined plane level. And let's say that is the case. And let's say the inclined plane it is at an angle theta with respect to the horizon. And let's say the surface is a smooth surface and we have an object. Let's say that is the case and the object is of mass m. And now because the surface is a smooth surface, it means there's no actually any sort of the friction force, you know, acting on the object. And let's say the object is you know, sliding down the plane. So what is the acceleration associated with the motion of the object on this plane? Now first thing you should have to understand about the forces, you should have to understand about the analysis of the forces acting on the object. So the object which is on the inclined plane, the forces acting are being analyzed as as it is being shown here. So the first thing, the force that is said to be existing on the object on the inclined plane, it is said to be the weight of the object. You know, the weight of the object is said to be acting in this way. So this is the weight of the object, which is given as the mg. We should have that. So that is the weight which is given as the mg. And now there is a normal force that goes like this. You know, a normal force is always perpendicular to the surface of the contact of the actually a plane, and it is given as n. So that is the normal force. And from there, according to the Newton's third law of motion, we have another force which goes like that. Now according to the geometry, this angle theta, it is the same as this angle theta. We should have that. And now we should have to look at the aspect of the two-dimension Cartesian plane. As you can see here, this is a typical two-dimension Cartesian plane. We have it as this. So where this is the x component and this is the y component, we should have it as that. So that is if you can look at it clearly. So which means, as you can see here, a weight of the object, it is at an angle theta with respect to the y-axis. So if that is the case, then we should have to resolve the weight into components, where we can have it as, we should have to resolve the weight into components where we'll have it as w cos theta. So that is the y component. That is the y component of the force. And since the angle it is against the y-axis, so in y-axis we'll have the cos. And what is the component along x-axis? We'll have it as the w, which is the weight, times the sine theta. We'll have it as that. So this is how we should have it. You know, the only force which is acting in the direction of the motion, it is this component of the force. And therefore, according to the Newton's third law, actually a second law of motion, a force is equal to mass times acceleration. But what is that force? We have it as the weight sine theta, and that which is equal to the mass times acceleration, like that. And of course, weight is given as the mg. You know, sine theta is equal to mass times acceleration. In all cases, this mass is the same as this mass. Hence, we'll have acceleration is equal to g times sine theta. So this is how we can have the acceleration of the actually object as it is sliding down. And from there, we can be able to have the distance traveled, its final speed as it will be hitting the surface in some sort of, according to the equations of kinematics, much as you know that one. So that's how we should have that understand. Now, how can you be able to calculate the normal force if that is the case? Now, since the motion is in x-axis, it means in y-axis there is no motion, hence acceleration is 0. So for that case, according to the Newton's second law of motion, force is equal to 0 since acceleration is 0 because there's no motion along x-axis, should be y-axis. And what are those forces? We have the normal force minus, W cos theta, and which is equal to 0. Of course, the normal force will be the same as, mg cos theta. So this is how we should have the normal force of the this is how we should have the normal force of the object in that case. So now, what if we have also the same case of the inclined plane? Let's say this is stromo atypical inclined plane. And let's say it is at an angle theta with respect to the horizon. And let's say this is stromo an object. Let's say it is of mass m, like that. And now, assuming that we have a force, let's say given as F being upright on the object, and the object is sliding up down. Actually, the object is said to be pushed up. And let's say we have another force given as, let's say this is F1, and let's say this is F2, like that. So how should you have the expression for acceleration of this kind of a system if that is the case? These are the upright forces. This is the F1, this is the F2, and they are the ones responsible to uplift the object to reach at the top. So what will be the acceleration for this case? Principle remains the same. Apart from these forces being upright, we also have the force due to the weight of the object that will go like this. So keep in mind about the analysis of these forces. So we have it as the weight, which is equal to the mg, and the principle remains the same. We'll have the normal force that will go like that, and we have the force that will go like this, and which is like that, and this angle is the same as this angle. Therefore, we'll have it as this case. And now we should have to resolve the weight into components. That will be given as the weight cos theta, and we have another force which is given as the weight sin theta. Stromo, despite that the object is moving upwards, but stromo, the x component of the weight, has to act downwards. It follows the direction of the gravitational force. So which means in the axis of the motion we have three forces responsible. We have F2, F1, and the x component of the weight of the object. And now, what are the forces acting in the direction of the motion? We have F2 that will be positive plus F1 minus W sin theta, and which is equal to the mass times acceleration. And now from this point we can be able to have what is the acceleration, much as we have the mass, the weight will be there, F1, F2 is there, then everything can be okay. And how about if we tend to look at the aspect of the normal force? Now, since there is no motion along actually a y-axis, it means the acceleration is 0. Therefore, we have the force being equal to 0. And what are those forces? We have the normal force minus W cos theta, that which is equal to 0. We have the normal force being given as, W cos theta, like that. So this is how the normal force can be obtained in that way. And how about if we have, let's say, in this case, how should you be able to analyze the aspect of the motion and of this object? Let's say this is stromo an inclined plane. Let's say this is the case of the inclined plane. Let's say it is at an angle theta with respect to the horizon, and let's say this is an object. It is of mass m. And now let's say we have a force being upright. let's say this is the force being applied given as F. It is being applied at an angle theta with respect to the horizon. Let's say that is the case, and the object is said to be moving up. Let's say that is the case. So how should you have the acceleration? I should say, let's say that is the case, a typical case in this case. But now let's say the object is moving at a constant speed, and the object is said to be moving up, but it is moving at a constant speed. So how should you have the value of the force being applied if that is the case? And now if the object is moving at a constant speed, so constant speed, it means the final velocity is the same as the initial velocity. And now for this case, acceleration is said to be 0. If the object is moving at a constant speed, it means acceleration is said to be 0, and therefore the final speed is the same as the initial speed. So keep in mind that the object is moving at a constant speed, its acceleration is 0, and therefore Newton's second law of motion will be given as the force will be equal to 0. And because the forces acting are balanced, so constant speed, 0 acceleration, balanced forces. We should have that. Now let's analyze the forces acting on the object and how we should have the expression for the force being applied. And our first thing, since the force being applied it is at an angle, we should have to resolve the force into components. Therefore, have to have it as this. This is the y component, and this is the x component, and that is Fy, and this is Fx. We should have it as that. Apart from this, we should also have to analyze the forces of the weight of the object. That is, weight is equal to mg. Now have the normal force that will go like that. Now we have this component of the force that will go like this. Now we have this one as angle theta, as this one is as well. We should have W, cos theta, and this is, we have the x component which is given as the W sin theta, in that way. And now, since the object is moving up, what are the forces responsible, or what are the forces that are acting in the direction of the motion? We have the weight that is going towards that is going against the direction of the motion. That is negative weight sin theta. And apart from that one, the x component of the force, it is the one which is acting in the direction of the motion. That will be given as the positive Fx, and which is equal to 0 since the object is moving at a constant speed. And that is, what is Fx? Upon resolving the F into components, we'll have it as negative mg sin theta and plus F cos theta, and which is equal to 0. Then from here we can be able to solve for a force being applied, and since we have the mass, if we have this angle and also if we have this angle, then the force being applied can be okay, and we can be able to have it. And how about how we can have the normal force? The normal force for that case, and since along y-axis there's no motion, what it tells us that the summation of the forces along y is equal to 0. And what are those forces? We have the normal force, and we also have that force which is acting downwards. We have it as the negative cos theta. And apart from that one, also have the y component of the force being applied, that is negative, since it is also acting downwards. We have it as Fy, which is equal to 0. But what is Fy? Now normal force is equal to actually mg, should be normal force minus mg cos theta, and minus, we'll have it as F sin theta, and which is equal to 0. So which means we can be able to have the normal force from that aspect. So keep that in mind. And now what if we have the friction force? So what can you say about that case? In this case, let's say we have, this is a rough surface, and let's say it is at an angle theta with respect to the horizon, and let's say this is an object of mass m. Let's say that is the case. And now, what is the acceleration for this object if we consider the friction force? And now since the object is sliding downwards, it means let's analyze the forces acting. We have the weight of the object, which is given us. The weight is equal to mg, and this is the normal force that goes like that. I should be have it as that. And now we have it as this, and that is that. And we should have to resolve the weight into components. We have the weight cos theta, and now we have the weight sin theta. And now since there is a friction force, and the friction force, since the object is moving, we have it as the kinetic friction force, which is given as Fk. So it will be acting against the direction of the motion. According to the Newton's second law of motion, the forces responsible for the motion are the ones that are acting in the axis of motion. We have the weight sin theta, which is acting in the direction of the motion, minus Fk, which is the kinetic friction force, is equal to mass times acceleration. But what is the weight? We have it as mg, sin theta. And what is Fk? We have it as mu k, and times the normal force, which is equal to the mass times acceleration. But what is the normal force? We should have to use the forces in y-axis. And since there's no motion along y, it means, as we already looked up that one, normal force is equal to the weight times cos theta, of which this is the same as mg cos theta. We'll have it as that. And therefore we should have it as mg times sin theta minus mu k, mg cos theta, which is equal to mass times acceleration. This mass, and this mass will go. Then we can be able to have the acceleration using this expression. So that's how we should have it in some cases, whenever we have it as we have the object moving on a rough surface like that. Let's say we have this kind of a case. What if we have a same case, but let's say it is at an angle theta. Let's say this is an object like that, and let's say we have the force being applied. We'll have it as, let's say, F1, and let's say we have another force being applied, let's say given as F2. Let's say that is the case, and the object is of mass m. So how should you have the acceleration of the object if the surface is a rough surface? And now since the surface is rough, it means there's a friction force on the surface. And now for this case, let's analyze the forces acting apart from these actually applied forces. And now we have the weight that goes down. That is given as the weight is equal to mg. You should have that. And we have the normal force that goes up. That is given as n. And we have it as this as well. And now this is also the angle theta, as we have it here. And now since the surface is a rough surface, it means there is what we call as actually a kinetic friction force that is said to be opposing the motion. And by the way, we should have to resolve the weight into components. We have this is the weight cos theta, and we have weight sin theta. And apart from this, we should also have another force, which is Fk. And since the object is moving up, it means Fk will oppose the motion. We'll have it as that. So what are the forces acting in the axis of motion? We have F2, which is positive since it is acting in the direction of the motion. We have F1 as that, and minus Fk, which is opposing the motion. And also we have W sin theta, and that will be equal to the mass times acceleration, if at all the object is accelerating. But if the object is moving at a constant speed, it means we'll have it as equal to 0. Then that is how we can have it. But now we can be able to have the acceleration using this expression. Much as we have everything, then the acceleration will be obtained easily, of which Fk we already talked about, it is given as the mu k times the normal force. It is always given. The normal force is the same as N is equal to W cos theta if we only have two forces acting along y-axis. So we should have that. What if we have the system of the connected bodies on an inclined plane? Let's say we have this typical case. Let's say we have this is a case that we should have to look up to. Let's say we have this is the object of, let's say, a mass 1, and let's say this is the object of, let's say, mass 2. And now let's say these objects are connected by the massless strings. Let's say these objects are connected by the massless string. Let's say that is the case. And now this is inclined plane at an angle theta with respect to the horizon. Let's say that is the case. And now assuming that the objects are moving towards this direction at a constant acceleration. So how should you have this acceleration? Assuming that the surface is a frictionless surface. Now for this case, we should have to analyze the forces acting. We should have to analyze the forces of the object on the inclined plane. We should have its weight, which is given as the weight 2, since this is object 2, is equal to mass 2 times acceleration due to the gravity. And we'll have its normal force calculated as N2, and since it is object 2, and we have it as that. Now this angle theta is the same as this angle theta, so which means this is weight 2 cos theta, and now we'll have weight 2 sin theta. We'll have it as that. So which means this component of the force, or the component of the weight, it is the one responsible, that is pulling the whole system downwards. So which means we'll have the tension force T1 and we'll have the tension force T2. That will go like that. So this is actually a weight 2 sin theta. It is pulling on this object, and now this object, it is the one which is pulling this object, and now we'll have it as the tension force T1, the one responsible to pull this. And according to the Newton's third law of motion, object 2 is exerting the same force but in opposite direction. We'll have it as the tension force T2. We'll have it as that. So let's start with the analysis on each object separately. So let's start with the object of mass 1. So we should have the free body diagram for the object of mass 1. And now this is the case. What are the forces acting on it? We only have the force 2, which is tension force 2. So we'll have it as this. So that is T2. And according to the Newton's second law of motion, it is the force responsible for the acceleration. Therefore, we'll have it as T2 is equal, should be mass 1 times acceleration. That is equation 1. And now we wish to go on the another object that is of mass 2. And what is that? And what is its free body diagram? We have, this component of the force which is acting in the direction of the motion. That is given as, weight 2 sin theta. And we have the tension force T1 which is acting against the direction of the motion. We'll have it as the T1. According to the Newton's second law of motion, it means we have weight 2 sin theta and minus T2. It should be T1 is equal mass 2 times acceleration. And this is given as equation number 2. And from there, we should have to add the two equations. And that will have it as, by the way, we'll have it as, a T2 is equal mass 1 times acceleration. Then we'll have, weight 2 sin theta minus T1 is equal to mass 2 times acceleration. So we should have to add the two equations. Let me have it here properly. We should have to add the two equations. Since T1 and T2 are the same, but they just have two different directions, it means upon adding them, they'll cancel. We'll only have the weight 2 sin theta is equal to mass 1 times acceleration plus mass 2 times acceleration. And from there we can be able to have the expression for the acceleration. You observe that the acceleration will be equal to W2 sin theta, and that divided by mass 1 plus mass 2. So this is how we should have the acceleration of the object, of the system. And from there we can be able to have the tension force T1 or else tension force T2. Of course they're the same, they just have different directions. So we should have that. What if, let's say, we have this kind of a typical case? Let's say we have the inclined plane at an angle theta, and let's say that is the case. We should have this. And let's say this is the object. Let's say this is the object of mass 1. Let's say that is the case. And now we have another object here. Let's say this is the object of mass 2. And let's say the two objects are connected by the massless string. Let's say that is the case, as you can see here. What should be that? And now let's say this is the massless string in that way. And let's say the whole system is moving towards this direction. Let's say the whole system is moving towards that direction at a constant acceleration given as A. So what are the forces acting on the system? And we should have, let's say, tension force. This is tension force T1 and this is tension force T2. By the way, we should have to start analyzing in this case. Now let's just start with the object which is on the inclined plane. And this is the weight which is given as the mg, of course. That we should have everything there. That is the normal force. That is normal force 1, since it is object 1. You have it as that. And this angle theta is the same as this angle theta. So we should have to resolve the weight into components. We have weight cos theta, and we have the weight sin theta as that. And now since the whole system is moving towards this direction, it means this is the force responsible. And by the way, this is the weight 1, mass 1. This is the weight 1. So that should be the weight 1. So which means this is the force responsible to pull this object. And now this object, it is the one which is pulling on this object with a tension force given as T1. And this one is exerting the same force. I'll have it as T2. Like that. And there is also the weight of the object 2, which is given as W2. Always keep that in mind. So we should have the great insight on the forces acting on the system. Otherwise, you may end up you may end up forgetting some forces acting there and thinking that the forces acting are the ones that you have specified, but there has to be several forces, external forces acting, that you should have to familiarize yourselves with. And now let's see analyzing the forces acting on each object. Let's just start with object of mass 1. And we should have the free body diagram. What are the forces acting? And now in the direction of the motion, we have the weight 1 sin theta. That will go like this. So that is the weight 1 sin theta. And now we have the tension force T1, which is acting against the direction of the motion. I'll have it as the T1. And according to the Newton's second law of motion, it means we'll have it as the weight 1 sin theta minus T1 is equal to mass 1 times acceleration. And that is regarded as equation 1. And how about on the object 2. And what is the free body diagram for that case? So on the case of the object 2, we should have the free body diagram for that case. And now of course we can have it as, and now what is the force acting in the direction of the motion? We have it as the tension force T2, that is acting as that, and we have the weight of the object, which is W2. Of course, if you wish, you can have to present the system where the forces will go like this. This is the weight, this is the tension force. It is okay. It is the same way. Whichever the way you may see it as to be, that is okay. And now the Newton's second law of motion will have it as d2 minus weight 2, which is equal to the mass 2 times acceleration. And now from this point we should be able to add the two equations. And what it does is that we'll add the two equations. What we'll have is that this weight, actually this tension force and this tension force will cancel. We'll have it as weight 1 sin theta minus weight 2, which is equal to mass 1 times acceleration plus mass 2 times acceleration. For this case, we'll have it as the acceleration will be the same as the weight 1 sin theta minus weight 2 divided by the summation of the two masses. We'll have it as that. So this is how the acceleration will be obtained. If we have this kind of a system, we should have to get it as that. So now, what if we have this kind of a case? How do you think we should have it? Let's say if we have, this is a typical inclined plane, and let's say this is angle theta, let's say theta 1, and let's say this is angle theta 2, and let's say this is an object of mass 1, and let's say this is an object of, let's say, mass 2, and let's say the two objects are connected by the massless string. Let's say that is the case, and the whole system is going towards this direction at a constant acceleration given as a. So what will be the expression for this acceleration? So let's analyze the forces acting. We have the weight 1 that go up like that, that is the normal force. Have it as that, and have this as that. So this is angle theta 2, and this is the weight 1 cos theta 2, and this is weight 1 sin theta 2. We'll have it as that. And now this object, this actually a weight is the one which is pulling on the object, and the object is exerting tension force T1 onto this. So this one also exert back the same force, so have it as T2. And you should also have to analyze the forces acting here, that we should also have the weight here. That is the weight 2, we have the normal force, and by the way this is the normal force 1, and this is the normal force 2, and for the sake of interest. And we should have, this is the angle theta 2, like that. It should be angle theta 1 rather. And this is the weight 1, should be weight 2, weight 2 cos theta 1, and we should have weight 2 sin theta 1. We should have it as that. And now what are the forces? We have them as this. And now we should have to start with, let's say, the object of mass 1. What are the forces acting in the axis of motion? We should have the free body diagram, and this is weight 1 sin theta 2, and we have the tension force T1 which is acting against the direction of the motion. And now Newton's second law of motion will have it as weight 1 sin theta 2 and minus T1, which is equal to mass 1 times acceleration. That is equation 1. And how about object of mass 2? What can you say that for that case? So what are the forces acting? So our storm will have to use the same analogy. We have the force which is acting in the direction of the motion. We have it as should be T2, which is given as this. So which means the other force which is which means this force is acting against the direction of the motion, which is W2 sin theta. So according to the Newton's second law of motion, what it tells is that we have it as D2 minus W2 sin theta is equal to mass 2 times acceleration. So that's what we have. Then we should have the summation of the two equations and have the expression for the acceleration and for that manner. And now what it does is that if we add the two equations, what we have is something about this tension force and this tension force will cancel. We'll only have the weight 2 should be weight 1 rather. We should have it as a weight 1, sin theta 2 and minus weight 2 sin theta 1 is equal to mass 2 times acceleration plus mass 1 times acceleration. And from here we can be able to have the expression for the acceleration, which is given as the weight 1 sin theta 2 and minus weight 2 sin theta 1 divided by the summation of the masses m1 plus m2. So this is how the analysis has to be, and from there we can be able to have the tension forces on whatever the interest. And now let's consider the aspect of having the friction force on the inclined plane case where the objects are connected. Let's say we have this case as well. Let's say this is a typical inclined plane. And let's say this is the object of mass m. And let's say we have another object that is being connected here. And now this is true more the case of the connected bodies. This is a mass 2 as that. And let's say the surface is a rough surface, so which means there is what we call as a friction force that exists there. And now let's say the whole system is moving towards this direction at a constant acceleration given as a. So how should you have the acceleration? But now since the surface is a rough surface, and now since the system is moving, it means the friction force, it is a kinetic friction force, and that one will oppose the motion. And now let's analyze the forces acting. We have the weight 1, and then we have the normal force equated as the normal force 1, and which is given as that. Let's say this is an angle, have it as the same as here, so that is weight 1 cos theta 1 should be cos theta, and then we have the weight 1 sin theta, of course. And now this force is the one that is pulling on this object. It means this object is the one which is pulling on this. That is the tension, actually a tension force 1, and we have the tension force 2. And also because the surface is rough surface, there is what we call as a kinetic friction force, which is given as Fk. Of course, we can also think of presenting it in the same string, but it is the same as having it as this. That is okay. So it will oppose the motion. It will be given as Fk, of course, so have it as that. Now let's start with the analysis. So have it as m1. What are the forces acting? We have the force which is acting in the direction of the motion. We have it as the weight 1 sin theta. And then we have the force, tension force 1, which is acting against the direction of the motion. And I will also have another force, which is a friction force, which is also acting against the direction of the motion. So which means these forces are acting against the direction of the motion. So according to the Newton's second law of motion, of course they are the ones responsible for the acceleration of the object. So therefore we'll have we'll have it as being given as, should be the weight 1 sin theta minus Fk and minus tension force 1, which is equal to mass 1 times acceleration. Let's say this is equation 1. You should be very careful there. You should be very careful in the analysis. You should be very careful. And let's go for the object of mass 2. And by the way, there is a weight 2 which is acting down. Now for that case, we have, according to the Newton's second law of motion, we have the tension force 2 minus weight 2 is equal to mass 2 times acceleration. And now if we add the two equations, what we have to yield will be given as, the tension forces have to cancel. We only have what is that as, W2 should be W1 rather. W1 sin theta minus Fk, and that is, and also minus W2, which is equal to, mass 1 times acceleration plus mass 2 times acceleration. What is Fk? Fk will be obtained from the forces acting in y-axis only for object 1. So along y-axis there's no motion for the object 1, and therefore, a normal force 1 minus weight 1 cos theta is equal to 0. Therefore, the normal force 1 is equal to weight 1 cos theta, and therefore Fk is given as mu k times the normal force 1. We'll have it as that. We'll put it here, then we'll have everything out. So that's the working principle behind this kind of a case. You should have understand that and understand. What if, let's say, you have the same case, but now it's something. Let's say we have the same case of the inclined plane. Let's say at an angle theta. Let's say this is an object. Let's say of mass 1. And let's say this is an object of, let's say, mass 2. And now the two objects are connected by the massless string. Of course, that is the case. And let's say the both surface as the rough surface. And let's say the whole system is moving towards this direction. So how do you have the expression for the acceleration if we consider the kinetic friction forces? Principle remains the same. Now for this case, we should have to analyze the forces. That is weight 1. We should have everything here. That is normal force 1. And that is angle theta. We'll have it as the weight 1 cos theta. And that is weight 1 sin theta, of course. We have the tension force T1. And now since the surface is a rough surface, it means there is Fk, which is acting against the direction of the motion. And now also in this case we have the tension force T2. And now since the surface is rough, it means there is also what you call as the Fk. And by the way, I'll call this is Fk1 and this is Fk2. We'll have them as that. And it is acting against the direction of the motion. Also, because we are considering the friction force, it means we should also have to consider the forces acting along y-axis on this object. So have the weight 2, and we'll have the normal force called as the normal force 2. We'll have it as that. And now, let's start with object of mass 2, first of all, which is this. So what are the forces? We have the tension force which is acting in the direction of the motion minus Fk2, which is equal to the mass 2 times acceleration. But what is Fk2? Fk2 will be given as the mu k2 times the normal force 2, of which, looking at the case, the forces that are acting along y-axis for the object 2, we have the normal force 2 as well as the weight. So of which normal force 2 is the same as the weight of the object. So have it as Fk2 which is equal to mu k2 and times the weight 2. We'll put it here, and should be that. Let me have this one as that. And what you can have is, or have it as being given as, d2 minus, that is mu k2 times weight 2, which is equal to mass 2 times acceleration. And this is equation 1. And let's go for the actually case of the object 1. Now what are the forces? We have the weight 1 and sin theta, and the minus tension force 1 and the minus Fk1, and which is equal to mass 1 times acceleration, of which Fk1 corresponds to have it as, the normal force 1, mu k1 times normal force 1, which is the same as mu k1 times, weight 1 cos theta. So that's how we should have it. So what it tells us is that we should have to substitute that one, or have it as, where there is Fk1, we'll have this expression. That will be given as weight 1 sin theta minus tension force 1 minus mu k1 weight 1 cos theta, is equal to mass 1 times its acceleration. Mass 1 times its acceleration. We'll have it as that. Then that is the equation 2 we should have to keep in mind. And that is equation 2 we should have to keep in mind. And then we should have the two equations. What we'll have to yield will be something about, if you add the two equations, what we'll have to yield, it will be something about this. And that is, if we add the two equations, what we'll have is, this tension force and tension force will cancel. We'll only have, that is weight 1 sin theta minus mu k2 weight 2, and that of minus mu k1 weight 1 cos theta, and which is equal to, now have mass 1 times acceleration, mass 2 times acceleration. Then from there we can be able to have the expression for the acceleration. We just have to take this one out, and since we have already done we are already done with that one. So what it tells is that we have the weight 1 sin theta and the minus mu k2 weight 2 minus mu k1, weight 1 cos theta is equal to mass 1 times acceleration plus mass 2 times acceleration, of which acceleration will be given as weight 1 sin theta minus mu k2 weight 2 minus mu k1 weight 1 cos theta, and divided by the summation of the two masses. So that's how we should have it. So for that case, and also, how should you be able to analyze this one? So I'll leave this one for you to keep it dry. What if we have this kind of a case? Let's say this is theta 1, this is theta 2. Let's say this is the object of mass 1, object of mass 2. Let's say that is the case, as you can see it here. Now let's say the system is moving towards this direction. Assuming that the surface is actually it is a rough surface, what would be the expression for the actual acceleration? So I want to see the responses in the comment section below, if at all you are able to. So that's how we start to understand about the analysis of the object which is moving on an inclined plane for this case. Thank you.